Okay, so this is Lab 7, and this is associated with Lecture 7, and that is Lab 7. We're going to start talking about KNN classification. And so because the lecture day was pretty long, I'm going to keep the lab nice and short and sweet today, and we're just going to see how far we can get into introducing some KNN regression, and we'll continue with this in the next labs, looking at this regression, because there's a lot we can do here. Okay, so the first thing we need is some data, and we're going to work with the iris data set. And so iris data set is the data set where it has measurements on these irises, flowers, sepal length and width, petal length and width. You can Google those if you want pictures of sepals and petals. And it has species. So Setosa, Virginica, and the versicolor there's a third species in there, right? So you can always get some summary information on your data if you just call summary. So this gives me some summary statistics on, so sepal length width, petal length width are quantitative variables here. And the species is a class, is a categorical variable here. So we can do some classification because we have 50 of each class, and we can try doing some classification. And we know at least one method now called KNN classification, and we know that it is approximating what the optimal classifier, which is called the Bayes classifier. Yeah. And so let's look at it in practice here. So to get the KNN classifier, we'll load the library class. You might have to install it. And there's a function in there called KNN. And this is K-nearest neighbors classification. And it behaves very similarly. KNN classification is a very simple method, powerful but simple. That behaves kind of similarly to KNN regression, but we're going to predict the majority class of the nearest neighbors instead of the just taking the average of the nearest neighbors. So what do we want to do? We're gonna subset our data set down just for visualization purposes. We're going to subset it down to 3 variables. Sepal, I can't spell, sepal length, sepal width, and species. Chosen pretty much an arbitrary, but I just want 2 variables because then we can plot things. And that's purely why I'm doing it. And I'm going to generate a, let's say, a test train split, right, or test validation split. Depending on terminology, people are very sloppy with that terminology. And so let's set my random seed to some numbers, just so this is repeatable. The setting my seed just sets up the any random thing from that point to be repeatable. And one way of doing this is I'm just going to randomize so if I do this, well, it's going to cause an error, but if I do that, right? So I'm just randomly ordering the numbers 1 to the number of rows in my data set here, right? And this will allow me to so let's keep going. This will allow me to build up my training set. And actually, let's just resample. Yeah, let's do it. Is that what I want to do? Yeah, let's do it this way. So let's get my training subset to be the first. What do we want? 1, 2. Let's see, the first third of my training of my rows, and my testing will be subset is just going to be everything that is not in my training subset. So I think I've done this before, right? And And so I can look at what these are. All right, so they won't intersect with each other. Okay, but I've got the subset in that I've kind of randomly, that's just, I mean, there's many idioms and ways to do this, but that is one way of generating some random rows so that I can build my training set. Let's call it train D for training data. It's my data set, and I'm going to pull up my training subset, and correspondingly my testing subset, or my validation, whatever you want to call it, is going to be, pull off the testing rows, my testing subset. And just as a quick check, I can test, look at the dimensions of those. So I have 50 in my training data, and I have 100 in my testing data, which makes sense because I chose a third of my data to be the training. Okay. That all said, now we can actually let's build our KNN model. Okay, oh, that's huge. Make that a little smaller. Okay. What do we want to do? So, very much like the KNN regression function, our call to KNN, we actually looked at the help function here as training set, test set. CL is the class, K is the number of neighbors, you can also get that Bayes probability, that maximum probability we talked about. Cool. So let's try this out. Let's build the model. Okay, so by training, I'm going to pass it train data set. This only wants the, I guess I should split the training X's and training Y's. So let's just do that. So that's my training X's. I do everything but the first column, because my first column of my data is the species, right? And so my train Y is just the first column, and my test X is everything but the first, and my test Y is just that first column, which is is the species. Okay, so let's actually do that. Okay, so now this is going to be easy to do. Pass my training X's. What else do I want to pass it? I'm going to pass my test data, which is basically what do I want to predict on? It's test X, and CL is what would be called Y, train Y's, and number of neighbors 5. Why not? It's a reasonably middling number. We have 50 in our training data set, right? So it's not huge. It's not 1, right? You can think about what's going to happen if we choose k is equal to 1. There's tons of parallels to KNN regression here about flexibility of the method, blah, 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 right? Same thing goes with k. We'll explore that as we go. Probably won't get to it in this lecture, but we'll explore it as we go. So KNN doesn't actually kind of build a model function, like it doesn't return a model object like LM does. It's like KNN regression, which just straight up gives us the predictions. So I can call it prediction for Y, right? And we can look at them, right? So there we go. There are my predictions. Let's look at it. So it predicts about a third into each, which seems reasonable because in our original data, if you remember, we go back up here, there's 50 of each, but then we split the test and training. So if we really did our randomization correctly, we would expect about, in our testing and training, to be about, we had 100 in our test data set, and if we really did randomization, we would expect about a third in each. So that looks like pretty damn accurate there, right? So one thing we didn't talk about in lecture, but we will next time, but we can preempt it here, is you could look at an accuracy, and you could maybe call accuracy as the percentage it gets correct. So one cute way of calculating this is, let me just back up here. So if I test y. Let's just first of all do a gut check. So our test y has 30 Setosa, 30 versicolor, 36 virginica. So we're getting something wrong because these don't perfectly match up, but it looks like it could be very close. If I look and say test y is equal, test the equality with prediction for y, that's going to be true when they match and false when they don't, right? Kind of element-wise. The cute little thing is if you apply a math function to booleans, true is false, it will turn them into zeros and ones. So if I like sum them up, that's how many it gets right. Or if I take the mean, that's the percentage I get right, which is the sum divided by the total number. So one could call this accuracy, and we'd get an accuracy of about 76%, which is one way that people evaluate these methods. Accuracy is you can think of as an estimate of the percentage we get right on new data, and this is actually testing data, so that's true. So we're just out about time here, but this is a really simple introduction to KNN classification. We'll look at some fun plots next time, and some other fancy ways of evaluating these things. But for now, we can stop here.